So again, let's greet Marvin with a small applause.
Thank you very much for the nice introduction. I have to choose one of the two screens for pointing, so let's see how it works out. So welcome to my talk. It's called Random Forest, the first choice method for every data analysis, and we'll see whether this is true. So I give a very, very brief introduction in Random Forest. I guess most of you know how it works. And then we'll analyze 10 common claims about Random Forest, give an overview of implementations of Random Forest in R, and close with discussion and conclusion. So first, how does the Random Forest work? So imagine you have here this simple data set where you have circles and squares, and your aim is to separate the circles from the squares. So here on the right, there will be a tree. You start with a root node where all your observations are in. Then you do a split on a vertical or horizontal axis on this data with the aim to separate these two classes. So you want to maximize the purity in the two partitions. And you continue to do that inside the partition. So here on the left, you do another split. This time it is a horizontal split. And you see that the purity in the partitions gets better. And on the right, you see that this builds a tree. And we continue and continue. And now we see that except here, you have almost pure partitions. And here you might maybe guess that if you continue splitting here to separate the remaining ones, that this might be overfitting. So that might not hold in other data sets. So now if you have a new observation here marked in red, you will classify this as a circle because the majority of observations in that partition are circles. That was a single tree. If you do a random forest, you grow several of these trees. Every tree gives you circle or square prediction, and you do a final majority vote, and you get your final prediction. So there's a slight difference to just creating several trees on the same data. That wouldn't make too much sense, but you create a bootstrap sample or a subsample, grow a tree on that, and additionally select a number of random features at every node. This is the so-called M-try value, and you do that several times. So these two random components, so first bootstrapping for the trees, and second selecting the variables for the splits, you have two components which makes the different trees very different. So it increases the variance of the base learners, and in the end you have an ensemble of weak learners to build a strong layer in the end. So that's the whole idea of this ensemble learning. And these two random components are very important for random forest to work so well. So you have several parameters, just a few of them. If they're really tuning parameters, we will discuss later. So you have a number of trees. By default, this is 500. And usually you increase the number for high dimensional data sets. You have the M-try value, I just described what it is. The default in some packages is the square root of the number of variables, but it can differ in other implementations. That's the same is true for the number of trees. And you should increase the M-try value for larger, or for high dimensional data sets, but we will also see that later. And you have the terminal node size. This determines the tree size. So you choose the small one usually for classification and the larger for regression trees. And you could instead also put an upper limit on the tree depth, or there are some other approaches for, this is essentially a stopping criterion, so how far to grow. So that was the very brief introduction to random forest, and we'll start with our claims. So the first claim is random forests work well without tuning. You often read that. And if you look at the publication by Philip Probst et al. Of this year, they say random forest is the algorithm with the smallest tunability. And they compared random forest with a Ranger package, GLMnet for the lasso, single trees and rpart, k-nearest neighbors, support vector machines, and XGBoost. So in detail, they analyze the different parameters of random forest and their effect on the performance. So the tunability here is the difference of AUC of a non-tuned random forest and a tuned random forest. So for example, this point here will give you an almost 0.05 AUC increase on one data set for if you tune the M-try value. You see first, these numbers are quite low. So that goes into the same direction that the random forest tunability is small, which is good. And you see that the most important variables are M-try and sample fraction. And these are exactly the two parameters that go for the random components I described. So M-try is the number of variables, and the sample fraction is how many observations you sample for each tree. So here you again see that these two components are very important. So I did a small simulation to see what happens for high dimensional data. So you see here two box plots for the prediction error, one non-tuned and one tuned random forest. And you see for the first facet here is 10 variables. And it doesn't make a big difference. So that goes in line with the Probst et al. Results that the tunability of random forest is small. But if I increase it here to 1,000 variables, then the difference is quite high. So the effect is the same here of a few variables and the rest is noise. And you see that it almost loses no accuracy in the tuned model, but the non-tuned model is quite bad. The reason is very simple. You have to increase the M-try value if you are in high dimensional data. So that's also my summary of the first claim. The random forest works well without tuning. I would say that's true. The exception of high dimensional data, the low signal to noise ratio, which is quite common, for example, in genetics. There it's important to use a higher M-try value or even to tune the M-try value. So let's go to our second claim, which is no need to scale or recode predictors. So for scaling, this is quite simple because random forest is invariant to monotonic transformations. It's also scale invariant. To give an example, imagine you have this data here in original, and by using splits in random forest or in trees, you can only separate between the values. And now if you scale that, it doesn't make a difference. You still have the splits between the values. And even if you do a log transform or something like that, it won't change. So for scaling, that's true. For recoding, it gets a little bit more complicated. So imagine you have a categorical predictor, and this is 1, 2, 3, 4, and you want to separate the odd from the even digits. And it's in the standard, I call it standard approach, and this is also called the partition approach. It's quite simple. So the algorithm checks all two partitions of the categories, and in one split, it's easy to separate here the odd and the even digits. If you do the naive approach, so just treat them as numbers, you will always need 3 splits for that. So no matter how you start splitting, you need 3 splits here, because you can only put this linear splits, and then in the end it will completely separate your 4 numbers. So, and you can imagine for a larger number of categories, this gets worse. And if you use the commonly used dummy or one-hot encoding, you have the same problem. So in every split, you can just separate one of the digits, because each digit will have its own coding in a variable in the dummy coding. And so you also need 3 splits here to separate odd and even. And there's a further idea is to order the categories a priori. And you can do that in every split. In that case, it's for binary classification and regression outcomes. It's even shown that this is equivalent to the standard approach, but it's faster. But you could also do it in the very beginning. So you order your categories by the average outcome and then treat it as just as numerics. And the major problem with the standard approach is that there's an exponential relationship, and the number of partitions gets very large quite fast. So in this example for 4 numbers, you have 2 to the power of 4 minus 1 minus 1, so this is 7 partitions. If you do the same equation for, let's say, all 28 EU countries, then you end up with this huge number here of partitions. And note that you have to evaluate this number of partitions in each node in every tree of the random forest. So you really have a computational problem in this case. And if you compare the performance of the different approaches, you see that the naive or ignore approach here performs quite bad. Also, the dummy coding performs quite bad, which is interesting because it's the standard for most other machine learning methods. And actually, in this example, the order once performs better than the other 2. So order split is to order again in every split, and order once is to order once in the beginning. The first 2 are equivalent, as I said, or you can prove that. But if you order in the beginning, you can still keep an order if there is an order, even in very at the end of the tree. So it can, in some situations, even increase your accuracy. So to sum up, you don't need to scale or recode predictors, and we even have a fast solution for a large number of categories. So that works quite well for random forest. Second claim is it works well on high-dimensional data. So if you look at the literature, you see that its ability to deal with small sample sizes and high-dimensional feature spaces. This is often said of random forests. And interestingly, the rate of convergence depends only on the number of strong variables and not on the dimension p. So this is actually saying you can add how much noise you want, and it won't change your convergence of the random forest, which is really, really, really great. So that's what the theory suggests. And I just tried it out. So I took the iris data set and ran in random forest, support vector machine, and the simple neural network. And here you see the performance is about the same. They're all quite good. And then I just added random noise variables. 10, 50, or 100. And you see that the random forest doesn't really care. The variance gets a little bit higher, so you have some outliers here. So maybe you have to increase the number of trees to get it more stable. But the support vector machine performs quite bad here, and the neural network is completely off here. So this is just a binary, not a binary, but just a classification with the misclassification rate, and it's below 0.5. So it's not working at all for this kind of data. And this is without tuning. So you might be able to increase a little bit with tuning, but you see that the random forest is still working well. So the reason for that is this so-called intrinsic variable selection. So this greedy splitting, it selects the best variable in every split. So how I explained it. But you don't have to fit any parameters, weights, or whatever for the other variables. So it selects in every node the variables, the important variables. So it has an included variable selection. And this also leads to fast computation because you don't have to fit weights or parameters or anything for all the other variables, which might be unimportant. But we'll see in the second part more on the computation times. So I would say it works well on high-dimensional data. Claim number 4 is random forests cannot overfit. So we already heard about this original random forest publication in 2001 of Leo Breiman, and he wrote, overfitting is not a problem, and random forests do not overfit as more trees are added. So from that, I would say random forests do not overfit. And I did again a small simulation. So you see the prediction error, you see the number of trees, and this one here is the training error, and this is the testing error on independent data. And first, if you stick to that definition of overfitting, you see here that at about 100 trees, it starts to stabilize, and the prediction error stays the same. So you could say it's not overfitting in that sense that the prediction error is not getting worse if you add more trees. But still, the training error is already 0 quite fast. So the training error is always smaller than the testing error. And this is also a definition you sometimes read on overfitting. So I would say the first definition makes more sense, but still adding trees does not hurt the generation error, that's true. But the training error is indeed smaller than the generalization error. So I give an undecided here because it depends on your definition of overfitting. Claim number 5 is random forest works for any kind of data. So here's a huge list of extensions. So you could say it works on many kinds of data. You have random survival forest for time to event outcomes. You have conditional inference forest if you want to avoid split variable selection bias. We'll see that later. You have quantile regression forest if you pointer. If you want to have quantile regression and not just simple classification or regression. You have transformation forest if you want to predict the whole distributions. You have block forest for multi-omics data. You have random forest for bounded outcomes. You have generalized random forest where you're very flexible with all these things, and many, many more. So there are many extensions for many kinds of data. I would say some are still missing. So for example, longitudinal data or such as repeated measurements or time series. There are some works on that, but I wouldn't say that this is really working so well. And you have the big problem of image, speech, and natural language processing. So we'll see more on that on the next slide. And I'm pretty sure you, in your daily life, you have some examples where the random forest is not working so well for some reason. So some specific kinds of data. So a little bit more on the image, speech, and NLP data. If you look at the publication by Wang et al. 2018, they write, methods like random forests regularly outperform neural networks in arbitrary domains, especially when the underlying data sizes are small and no domain-specific insight has been used to arrange the architecture of the underlying neural network. And this point here highlighted in bold, I think it's very important because that's exactly the reason why deep learning works so well for these image, speech, and NLP data, because you use convolution neural networks or recurrent neural networks, which kind of put in that domain-specific insight. This might be also possible in a random forest, but at least so far, it's not working so well. And you see that all top benchmarks for these kind of data, they're almost completely deep learning and no random forest in there. So I put a small almost in that sentence. So It works well for almost any kind of data, with the exception of image, speech, and NLP data. Claim 6 is, you read that very often, random forest is an interpretable model as an advantage over other black box methods. And I would say a single tree is easily interpretable. So in this example, you split your data on sex, so male or female, on age, smoking. It's just an example I made up, but you can interpret this. It might get it a bit harder if the tree gets bigger, but still it is possible. And you even have the differences of purity in all the nodes. So you can say the split on sex is very important, and the one on smoker is not super important here. But for a whole random forest, how should you do that? You could look at every tree, but would you then pick a single tree and say this is important, the other one is not? So there might be some ideas to do that, but I would say in general, this is not easily possible. However, there are several variable importance measures available. So you have the simple Gini or impurity importance, which sums up these values here with the delta. So these values of a variable. You have a permutation importance, where you just permute a variable and look at the difference in prediction error. You have a bias-corrected impurity importance, because we'll see that in the next or after that claim that the Gini importance is biased. And there's a bias-corrected version of that. There are methods for conditional variable importance. There's also a method working completely different. This is the maximal subtree method, and some more. So I wouldn't say random forest is an interpretable model per se, but you have several variable importance measures available, and this is usually more than for other methods. So like for boosting, you have maybe 1 or 2 or 3 methods, and they're kind of the same as in random forest, and they're not working so well. And for neural networks, you usually just use the model agnostic approaches. So claim number 7 is the statistical properties are well understood. So there are results on consistency. So a single tree is not consistent, but a random forest is, if you put a limit on the subsampling rate. So the subsampling rate has to, at the same time, grow, but grow slower than the number of observations in your data set. You also have results for convergence rate. Interestingly, that's in the second sentence here, more noise even reduces the convergence rate. I don't really know how this is possible, but they showed that it is. You have results on asymptotic normality. So if you're subsampling and not bootstrapping from the single trees, you can show that random forests have asymptotic normal predictions. However, you need some assumptions for that. So first, you have to use subsampling or bootstrapping. You have to put a limit on your subsampling rate, which is often in conflict with the best prediction performance. And some of the results were obtained for a so-called purely random forest, where you remove the greedy component. So you select the variable just randomly, and you select the splitting point just randomly. So then you have a purely random forest, and this is easier to analyze, but it is also not the default setting, or not the standard random forest, far away, and it's usually worse in prediction performance. So yes, the statistical properties are well understood. There are several results available, but the assumptions might not hold with default settings, and you might lose prediction accuracy if you are in the settings where they hold. But still, for example, asymptotic normality, I would say it usually holds. Claim number 8 is the split variable selection is biased. So an example to that, or just as an explanation, if you have more splitting points, then this variable will be preferred just by chance. So as an example, you have a similar data set as in the example before. You have sex. This is just 2 unique values, could be more. You have medication type, which in this example has 5 unique values. For age in years, this is M unique values, which here is smaller than N. And you have a biomarker where all values are different. And now the biomarker will be preferred in the splitting over medication type or sex, just because it has more possible split points. Just by chance, there's a better chance for this variable that you find a split which is meaningful for the outcome is higher than for the one with lower categories. If you do a simulation study for that, it looks like this. So you have variables with different numbers of categories, and here the Gini importance is more or less the selection of in the splitting, and you see that the importance just increases. So the variable with more categories is preferred. And imagine now you would have this variable sex here, and it would have a small effect. Then it might be here. And this would be a true effect. All others are not true effects. So you would completely miss that. It would completely get lost in all the other variables. And interestingly, you see the same for the category frequency. So not only for the number of categories, but also for the frequency, which is even more common than different numbers of categories. Good news is we have solutions for that. So we have randomized splitting rules. So where you select the M-trie variables and you just select a random split point for each of them, and then use the best of them. So it's not like purely random, but with a random component, and you only have one split point per variable, so it's a fair comparison, and you don't have that bias anymore. You could also use conditional inference forest or maximally selected rank statistics, where the idea is to do an association test of the variable and the outcome, then select the variable with the smallest p-value of that association test, and then use the best split point of that variable. And because you compare on the p-value scale and not after the greedy splitting, you will also have an unbiased variable selection. And if you're mainly interested in variable importance and not in prediction performance, then you could also just use the bias-corrected variable importance, which doesn't solve the problem while splitting, but afterwards when you compute the variable importance. So I put a check mark here. The split variable selection is biased. This is true, but this is solved. Claim number 9 is performance is not state of the art. So some people say, you still use random forest. This is an old method. It's so 2005. Why don't you use this fancy deep learning method? And an interesting result on that is this benchmark of automated machine learning algorithms on 39 datasets and with a 4-hour time budget. So they analyzed several datasets, compared different AutoML approaches, and you see, if you look at the rank, and they added random forest just as a benchmark, just as a baseline. You see that H2O AutoML works quite well, and also AutoSKLearn outperforms the random forest, and the AutoWeaker doesn't work so well. So based on that, I would say, yes, random forest is not state of the art. These AutoML approaches are better. But if you now look at the actual AUC, it's not that clear. So yes, H2O AutoML performs better than random forest, but it's very, very close. And the random forest took on average 16 seconds and not 4 hours. So it might not be such a bad approach to compare to this AutoML approaches. So I again give an undecided here. The random forest, if you take implementation time into account, if you take computation time into account, it is state of the art. But usually your best performing algorithm is if you compare a lot of them and include some AutoML approaches and so on, random forest won't be the best. My last claim is random forest detects interactions. You also read that quite often. And I have some quotations here, and they all go in this line that random forests take interactions into account, but they won't detect them. And also written here, they get lost in marginal effects. So to explain that, you could look at these two examples. On the left, you see a data set where you won't find a first split. So this clearly is an interaction between x1 and x2. And it's very simple. If you have two splits, you split here, and it's perfectly separated. But every split you try will always have no change in purity in the subpartitions. So if you use a single tree here, it will just stop, make no split, and say no improvement possible. In a random forest, it might still work because you use tagging and you are subsampling, and you maybe exclude this observation, and soon this is a good split, and so on. But you won't do this and this at least not in a standard tree or forest. And on the right, you see no linear split. So the best split here would be like this. But you can only split vertically or horizontally in these trees. So you would need some rotation forest, or however you call it, where it's possible to split non-parallel to the axis. But here, it is possible to separate them, but you need to split here and here, or here and here, and again, you just need a lot of splits. And if you imagine you go to higher dimensions, then you really have a problem. So the problem is that the curse of dimensionality is worse for interactions. So you have just a low probability to select the interacting variables. So I put an example here for 10,000 variables, 100,000. If you choose the default M try value, then to just select two interacting variables after each other for the M try. So I'm not talking about selecting, so finally splitting on them, but just making it possible to split on them. You have a probability here of 0.00001, or for three-way interactions here, it's even worse, and then really get the small number. So it's very hard to find these interactions. If you increase the M try value, it gets way better, but still you won't split, because if you have no marginal effect, that's what I explained on the left in the last slide. Without a marginal effect, you won't split. So this example here, that you had to split here, but you have no marginal effect, so you won't. And with that, you might be lucky that your interaction is taken into account, and it usually works if you have a marginal effect, but if you don't, then it's not working. And detecting is not working at all. So I would give another undecided here, because it takes interactions into account if you have marginal effects, which is, I have to say, the more common scenario. So usually interactions go with marginal effects, but you cannot detect interactions. So then we come to the second part, which is about different implementations of random forest in R. And you have several of them. So implementations of Breiman's original random forest, you can find random forest SRC, arborist, and ranger. There have also been big RF and random jungle, but these two are not available anymore. And if you go to extensions, you have several more. So you have Party and PartyKit for conditional inference forest. You have Quantrack forest. You also have Quantrack Ranger for quantile regression forests. But that's not also included in Ranger, so actually you don't need it anymore. You have transformation forest, you have block forest, generalized random forest, and I guess some more. But we'll stick to the original random forest implementations in a comparison, because it makes no sense to compare completely different approaches in sense of computational performance. And let's start on low dimensional data. So if you have 100,000 samples, 100 variables, 1,000 trees, and the default mtry of 10, and we use multi-core with 12 CPU cores. And you see that, so here's the runtime for binary and for continuous variables in the memory. And you see that the random forest package is always a bad choice. So it's very slow for binary variables. It's also slow for continuous, and it uses quite some memory. You can speed it up with multi-core or whatever other approach, and then combine later the smaller subforests. But still, it's slower than others. Random forest SRC is not performing so badly. The arborist is very fast on continuous variables. So pointer is not. So you see that in the second column that continuous variables, arborist is the fastest, but in the first column for binary variables or general for categorical variables, the Ranger is fastest. And Ranger uses the lowest amount of memory here. If you go to, oh yeah, this is, so we originally published in our 2017 JSS paper this comparison, and since then, the random forest SRC really increased in prediction in computational speed. So they really did some improvements, and now it is quite fast. So that's a big difference to that original paper. And another strange thing is that the arborist is faster on continuous variables. So I would say it's always easier and faster to split on binary variables than on continuous variables. The arborist has quite some optimizations for that case, so it even works better than for binary ones. If you go to high dimensional data, so this is extremely high dimensional. So 10,000 samples, 150,000 variables, and 1,000 trees, and the mtry value here is larger than the default because we have seen that that makes sense. And you see here that the random forest takes almost 4 days and 50 gigabytes of memory. So you have to have quite a big machine to be able to compute this and wait for 4 days. If you try to use multi-core, it's obvious. I had 96 gigabyte RAM on that machine, so it won't work. I tried and it crashed, obviously. The random forest SRC was quite fast with 1.59 hours, but used quite some memory. The arborist also crashed because of memory issues. And if you use the specialized GWAS mode, which is optimized for this kind of data in Ranger, this takes 20 minutes. So not 4 days, but 20 minutes. And there's almost no memory overhead. But this is maybe a little bit unfair comparison because this Ranger mode is optimized exactly for this kind of data, which the others didn't. So a fairer comparison would be for this one, but it's still the fastest and the most memory efficient. And just as a note, if you compare with the original paper, I don't have access to that machine when we wrote that paper anymore. So the note here on the bottom. So these numbers are just a little bit larger because the machine is slower. But it shouldn't change the interpretation. So let's come to discussion and conclusion. To summarize the first part, pros on random forest are there's little or no tuning and data recoding required. You have good performance on almost any kind of data. Overfitting is not a major problem. So you can just use how many trees you can computationally afford. Variable importance measures are available and several good methods for that. On the other hand, you have bad performance on image, speech, and NLP data, random forests are not per se interpretable, and usually you won't win any prediction challenges with it. Because it's often a very well-performing approach, it's fast, it's easy to implement, and so on. But you will usually find, if you have time and computing power, another method which is better than the random forest. On the implementation side, I would suggest to use the arborist for continuous features and large sample sizes, which is quite common, and the ranger in all other cases. And if you have genome-wide data, then obviously also ranger is a good choice. But be careful, the packages not only differ in the default settings, they also differ in results. So even if you try to find the exact same settings, sometimes the results are a little bit different. For example, the arborist by default, if you don't change the settings, it's even faster, but it puts by default a limit on the tree depth, which might be good in some cases, but might be bad in other cases. So just be careful, not just switch the implementation and expect the exact same results. They are different in some parts, but for the ranger, we have shown that it leads to the accept random error, the same results as the random forest package. And the performance heavily depends on data, type and size of data. So never trust a benchmark where someone claims his new implementation is faster than everything else and just runs it on one data set. So we have seen that it really makes a difference if you have binary continuous data, if you have low or high dimensional data. This is really important for the computational performance. So in conclusion, is random forest the first choice method for every data analysis? I would say it's a good first choice for most data analysis. So it's always good to start with the random forest, but as I've explained, if you are after the best possible prediction performance, then you might end up with another approach. But still, it's a good idea to have to start with the random forest as some kind of baseline or benchmark. Okay, that's it. Thank you, and I'm open for questions.